Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about entanglement, quantum mechanical entanglement, and how to calculate probabilities when you are dealing with entangled quantum mechanical particles. Entanglement is one of the most mind-boggling and important ideas in quantum mechanics. It's at the root of what makes things like quantum computing possible. So let's dive in. So I want to start by introducing the idea of entanglement with a story. This is an example that Frank Wilczek gives in his nice Wired magazine article. And let's imagine. So I'm going to describe entanglement with a purely classical story to give you the essence of what entanglement is. So imagine that. Uh, there are two people, Alice and Bob, and they have kitchens. So let's start off with an example. They have separate kitchens, and each one of them owns two cake pans. One is a square-shaped cake pan, and the other is a circular-shaped cake pan. And imagine that each day, Alice reaches into her cabinet where she has her cake pans and she randomly pulls out one of those cake pans, and Bob does the same thing. And so each day, we look at the cakes that Alice and Bob have baked, and we'll find that 50% of the time Alice bakes a square cake, and 50% of the time she bakes a circular cake. Same for Bob, but those results are completely uncorrelated. There's no knowing something about what kind of cake Alice baked tells you nothing about the kind of cake Bob baked. So if you go through the sort of probability tables, a quarter of the time they'll both end up with square cakes. A quarter of the time they'll end up with circular cakes, etc. But there's no correlation between the results. And so we would describe this as a unentangled system. Unentangled. Separate kitchens. Now imagine that Alice and Bob move in together, and they share a common kitchen. And let's suppose they have just one square cake pan and one round cake pan, and each day they decide to bake a cake. So one of them reaches randomly into the cupboard, picks a cake pan, and then the other one bakes a cake of the other shape. And then, of course, in that case, 50% of the time Alice will end up baking square cakes, and 50% of the time she'll end up baking circular cakes. But now the results are highly correlated. Whatever shape Alice bakes, Bob is going to get the other shape. So this would be a completely entangled system. And point out, these kinds of correlated or entangled results are very common in the classical world. So, just to pick a random example, in the 2016 election, 51% of the voters voted for Hillary Clinton for president, and 49% of the voters voted for Mike Pence for vice president. But as far as I know, the way you calculate the percentage of people who voted for Hillary Clinton for president and Mike Pence for vice president is not 0.51 times 0.49. This is zero, because you couldn't vote for Hillary Clinton for president and Mike Pence for vice president. So that's just a random example. But sort of correlated or entanglements are just a very common thing in the classical world. And in the unentangled case, where you sort of get the probability of the joint event by independently multiplying the two individual probabilities, when things are correlated, that rule doesn't work. And that sort of distinction between entangled cases and unentangled cases is going to carry through to the quantum mechanical case, with the twist that when we calculate probabilities in the quantum mechanical world, the rule is that we have have to calculate these probability amplitudes and then square the result. And calculating the probability amplitudes allows for the possibility of interference effects, which is something that's quite quantum mechanical. And there isn't a good analog of that in sort of classical probabilities. And also point out that the entanglements or correlations are not always complete. To take this voting analogy, sort of similar, you might say that 51% of Americans in 2016 voted for Hillary Clinton, and 70% of Americans are pro-choice or something like that. But the probability of voting for Hillary Clinton and being pro-choice is not 0.51 times 0.7 because there's a strong correlation. It's not a complete correlation, but if you voted for Hillary Clinton, you're much more likely to be pro-choice than if you didn't vote for Hillary Clinton. And then, so that's all classical. If you really want to get at the root of what's spooky about quantum mechanics is you imagine that Alice and Bob have separate kitchens, spatially located kitchens, and somehow they're in the rules are such that Alice is reaching into her cupboard and picking a shape for her pan, and then somehow whatever shape she picks, Bob gets the opposite shape. So that's the sort of spooky action at a distance that was so troubling to Einstein about the rules of quantum mechanics. Okay, so that's the background. So let's go from the classical world of baking cakes to the quantum mechanical world of photons. So let me describe situations which are the quantum mechanical analogs of the stories that we just told with Alice and Bob baking cakes in their kitchen. So the first story involves a experimental situation which should be familiar to you. It starts off like the experimental situation that was described in the American Journal of Physics article that you read about single photon interference. So we're going to imagine a situation where we create pairs of photons. And the way we do that, remember, is you have some nonlinear crystal, this BBO crystal, you send in an ultraviolet or near ultraviolet photon, and there's a process called spontaneous parametric downconversion that occasionally creates this 405 nanometer wavelength photon generates a pair of infrared photons. And we're going to focus on the polarization states of these photons. And it turns out that if the ultraviolet photon here is polarized in the direction, in the vertical direction, then you're going to get the infrared photons that are generated are both going to be horizontally polarized, as is shown here. And in this first situation that we're describing here, the polarization states of these two photons are unentangled, and unentangled in the sense that making measurements on one of the photons doesn't give you any information about what measurements made on the other photon are going to yield. And so we can think of these photons, and we call them the signal photon and the idler photon. So there are subscripts S and I here to stand for signal and idler. We could think of the signal and the idler photons as existing in two separate worlds, two separate Hilbert spaces mathematically. And so we could describe the two photon polarization state with the following notation. We're going to introduce what's called the direct product. And you can think of what the direct product being is it's an indication that the thing on the left-hand side of the direct product is one Hilbert space, and the thing on the other side of the direct product is the other Hilbert space. These are sort of two worlds that are not correlated with one another. And a shorthand notation for this direct product relationship is to describe the two photon state This is the notation that Beck uses. We put inside the ket, we put an H comma H, and the first position here corresponds to the state of the signal photon, and the second one corresponds to the state of the idler photon. And the logic can flow in the other direction. When two particles are unentangled, we can write the overall quantum mechanical state as a direct product of two single particle states, as is shown here. And as an example of how to calculate probabilities when you have unentangled particles like that, let me imagine the following situation. Suppose we take a pair of polarization analyzers, which are constructed so as to measure the polarization relative to the 45-degree direction. So a photon comes in and it either comes out the plus 45 or the minus 45 port, and I place one of these analyzers in a position to measure the signal photon, and the other analyzer I put in a position to measure the idler photon. And then suppose I want to calculate a kind of joint probability. So the particular example is, what is the probability that if I perform measurements with these two polarization analyzers, I find that the signal photon comes out of the plus 45-degree port of this analyzer, and the idler photon measures minus 45, which means that it comes out of the minus 45-degree port on this analyzer. And our approach really is quite similar to what we did in the single particle case. The probability of this occurring is going to be equal to the magnitude squared of some probability amplitude, but now the probability amplitude involves these two particle states. So you could think of it as this probability amplitude inside here is the projection of the H comma H state onto the state plus 45 and minus 45. And the question is, I want to come up with a numerical answer for what's the value of this joint probability amplitude. And the answer ends up being pretty simple in the unentangled case. It's sort of exactly what you'd expect when the two particles are existing in separate worlds. The joint probabilities are just the product of the individual probability amplitudes. The joint probability amplitude is just the product of the individual probability amplitudes. And that ends up, numerically in this case, it's easy to see that each of the factors here ends up being equal to 1 over the square root of 2, so that the joint probability amplitude is 1/2, and then when you take that and square it, you get the probability is 1/4 in this case. That ends up being the answer. So that's the unentangled case. What about the entangled case? So experimentally, it turns out we can generate two photon states that are entangled using just a slightly different crystal in this position. So now we're going to generate a signal and an idler photon, but the two photon state is going to be entangled or correlated. We're going to describe the two photon state as a superposition of a state in which both the signal and the idler are horizontally polarized, and a superposition of that with the state in which they're both vertically polarized. So now the way we calculate probabilities is a little bit different. So let's see how that works. So the first thing to say is that if you make measurements of polarization with respect to the H and V directions, then it's immediately obvious what's going to happen. If you measure with respect to the HV basis, half of the time, you're going to find out that both photons end up being polarized horizontally, and half of the time, you're going to end up finding out that both photons are vertically polarized. What about a calculation when you make measurements with respect to the plus or minus 45-degree directions? So we're going to take two photon pair that is in this entangled state, and we're going to send the signal photon into this analyzer and the idler photon into this analyzer, and we're going to ask about how you calculate probabilities. So we proceed as usual. The probability of measuring plus 45 degrees for the signal photon and minus 45 degrees for the idler photon. We're going to need to calculate this probability amplitude here and then take the magnitude squared. So what is the right way to calculate this joint probability amplitude? So if we write things out, what you see is because the state that we're dealing with is a sum of two terms, we get this probability amplitude that we need to calculate is the sum of two different probability amplitudes. Well, we just evaluated the first one, and we showed that it was equal to plus 1/2. It doesn't take much effort to evaluate the second one. If you proceed exactly as we did before, you'll find out that it is equal to minus 1/2. And plus 1/2 and minus 1/2, when you add them together, you get a 0. And so that's a result that's quite different from the experiment where we had just an unentangled photon going in. And it really is significant in the sense that what we're seeing here is a type of interference. When you have a situation where you have to add probability amplitudes, in general, they're complex numbers, but even in this case, you have a plus and a minus, and they add to 0. So you can think of that as a type of interference. And this really is a good example to look at because it shows that when you deal with entangled states, interference effects can be really important. And as you'll see down the road when we talk about quantum computing, that really is the root of the whole ball game that we play. We take advantage of these kinds of interferences when you deal with entangled states. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye-bye.